There is a lot of talk today about thermal interface materials and, there was at one time a lot of talk about graphene and nanotubes and now diamond and then microchannels for cooling, just if the thermal space, for example. So there are startups looking at single-phase cooling and two-phase cooling, looking at localized pool boiling as a ways of effective heat transfer, coming up for these high-power devices. So I would say there is opportunity for startups in these niche areas where you don't have to be a big person on the block, but there's definitely opportunity. So materials, measurements, simulation, all of these things. So.
Namaskar and welcome to another episode of the Professor Mahesh podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified. This podcast is brought to you by IIT Madras Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global is our platform to take everything IIT Madras and largely everything India to the global audience, our thinking, our research, our teaching, our startups, our entrepreneurship, our philosophy broadly. Come learn more about IIT Madras Global's efforts in the link in the description below. India, as we all know by now, is on the cusp of a semiconductor revolution. What exactly is this semiconductor revolution? What is under the hood? What sort of new jobs are likely to be created 4 or 5 years from now, maybe even 10 years from now? And what are the technologies that are going to be absorbed as part of this semiconductor revolution? To help us parse this space out a little bit, with particular emphasis on semiconductor packaging, I have a distinguished guest, a long-time Intel person, Dr. Gaurang Choksi. Thank you, Gaurang, for making the time to be with me on this conversation, on this podcast. Let's start with a little bit of your own training. Where did your life start as an engineer? And we'll go from there.
So I spent all my life growing up here in Chennai, actually, in Adyar, not too far from here. I went to school here. I did my undergrad here, and then in Chennai, and then I went to grad school in the US, and my degree is in applied mechanics. My PhD is in applied mechanics, and then I joined.
We are here in the applied mechanics department.
Exactly right. So it's very nice. And I joined Intel right after graduation in 1988, and I spent almost 4 decades in the packaging business at Intel, and I retired December 2024 from Intel.
So we're talking 1985 Intel, roughly.
1988, yeah, 88.
Right, that must have been a very exciting time to be part of Intel.
Yes.
Tell us about the Intel of 1988 and the 1990s.
Yeah, actually Intel had just come out of the big DRAM challenge which Intel had faced. It's a very challenging time for Intel. And I joined Intel soon after that. And this is when the Intel 386 chip was out and gaining ground. And my first project was Intel, the 486 chip. So I was working on the package design team of 486. It's a very exciting time, like you said, and I was fortunate enough to be a part of the growth and the boom in the industry and at Intel, from the 486 to the Pentium Pro, all the way out to where we are today.
Tell us a little bit about your graduate studies. You studied in the Department of Applied Mechanics. Tell us a little bit about what you did there.
I did my PhD at Virginia Tech in the Engineering Science and Mechanics department, and my PhD work was more on the fracture of composite materials and computational mechanics. And the reason I joined Intel was there was an opportunity there to go look at ceramic packaging, and then they were trying to look at the fracture and failure of packaging. It's a multi-layered material, very similar to the aerospace composites, where I did my PhD work in.
So is mechanical fracture anywhere near a problem in chips?
Yes. So if you look at the packaging itself, packaging has, it has to withstand what we call the end-use conditions. So you have shock, vibration, thermal cycling. So very, very typical applied mechanics type problems. So everything that we learned in school in terms of materials response, structural integrity, they all get applied here.
So let's step out and just first understand this whole semiconductor value chain, right? I'm assuming a chip starts out as a design, right? So can you help us walk through the whole process by which possibly I see it in a mobile phone, some years after a design?
Yeah. So yes, you have the chip design process, which by itself is a fairly complex process. You go through an abstractization of what you want the chip architecture to be, and then it manifests itself in a physical layout of the chip itself. But there's a lot of intermediate steps related to design, analysis, validation of what you're trying to make, and that works very closely, the design process, with where the chip gets manufactured, what we call a wafer fab. And the wafer fab has associated design rules related to manufacturing. So then you have to integrate these design rules, which are for manufacturing, along with your design tools. And there's an entire industry called the EDA industry, the electronic design automation industry, which then creates these tools for making sure that you can do the design and the design is relevant to how the manufacturing process works, so that when you manufacture the chip, all the considerations for a high yielding process and the chip comes out functioning as best as you want it to function. Once that is done, then it goes through what we call an assembly and test process. And today, the complexities of, even if you take a cell phone chip, it's got multiple components to it. And you have now multiple components you need to optimize. And the back end of the whole process is what we call semiconductor packaging. And today, what happens is you have to make sure that you're partitioning the architecture of the overall system upfront during the chip design phase. So you have the chip design and package design. What you have to do now is there are companies called EDA companies, electronic design automation companies, that actually integrate design flows. And there's been a lot of, I would say, consolidation in some of these design tools, where you can now get a full suite of tools which starts from all the way from a chip architecture to board design. And it's part of one big suite. And there is interoperability between these tools so they can talk to each other. And so what you do then is you optimize or you co-optimize your package layout, your package footprint, along with your chip footprint, so that now you're globally optimizing the entire, what we call the interconnect, all the way from the chip level to the motherboard level. Once that is done, then you go into what we call assembly and test process. So this is what we call the back end of manufacturing. The front end is the wafer fab, and the back end is assembly and test. So once the chip is made in the wafer fab, you get this big wafer from the silicon fab, and then it's individually cut into individual chips because you have multiple chips on the wafer. And then that goes into a separate factory called the assembly and test factory. And there you assemble these chips onto a package using different techniques, depending on the technology and the complexity of the chip you have. And then it goes through a test process. And once it passes all the tests, then you can send it to the customers who would buy these chips.
So just so our listeners can get a complete grasp on this, can you give examples of the leading players for each of these steps? Start again with the design. So design would be in the hands of companies like Intel or Qualcomm's.
Fair enough. So there are actually two types of companies who get involved with this. One is companies that are vertically integrated like Intel. They're called integrated device manufacturers, or IDMs. So they would design the chip, design the package, and in-house make the chip, assemble the package, test it, and then send it to the customer. So these are very vertical, integrated companies. They have all the competencies and all the collaterals they need within the company itself. Then you have companies that are companies like Intel, Samsung are examples who are IDMs. And then you have companies who are called fabless design companies. So the NVIDIAs, the AMDs, the Qualcomms, the Apples of the world, they design the chips. They have good competencies in chip design, but they work very closely with their partners who are the manufacturing arms like TSMC, for example, who would make these chips for them. And then they would give these chips once they get from TSMC. Either TSMC now has packaging capabilities of their own, so they can do the entire manufacturing process for their customers like Apple or NVIDIA or AMD. Or you also have an entire ecosystem called OSATs, where they specialize in assembly and test of these chips from companies like Samsung or TSMC. So they would get these chips from these fabs, silicon fabs, assemble and test them for customers like the fabless companies.
Okay. So in this whole process, companies like TSMC has, they have investments in machinery. So let's talk a little bit about who makes this machinery and what are these machines that actually make silicon functional.
So a lot of companies now, the fab process has multiple very complex steps, as you know. And as the feature sizes scale with respect to, silicon level scaling, what happens is the time it takes to develop these new technologies, the cost of making these technologies goes up very quickly. So that's why each successive silicon node, as we call it, for scaling down, ends up in a lot of folks who are these large players who also end up making some of these tools. So, for example, there is this technology called extreme ultraviolet lithography. So, get to very fine scales, you need a new type of lithography. So there's a company called ASM in the Netherlands who specialize in this equipment. Then along the same lines for different process steps, there are a lot of different companies. There are companies like Nikon, etc., who make the steppers. So there is a whole bunch of, there's KLA, there's Applied Materials. All of these companies are very large companies. They also have small companies who specialize in a specific tool. And then you have startups that come in and try to get over some of these markets. In parallel to the processing equipment, there is an entire subsection of equipment suppliers who work on the metrology and measurement equipment. So your process is only as good as how you can measure the process. So you have to make sure that, as you're scaling these dimensions down, your metrology is keeping up with it, not just from a capability point of view of measuring the feature size, but also from a volume production. So you want to measure X parts per minute. And if the feature size is getting smaller, how does the sensor world keep up with it? I need new optical sensors, for example. So that's an entire ecosystem. This is where you can get academia, universities, etc., playing a role, and also coming up with the next generation of sensors, for example. That kind of whole thing fits in. It's a pretty complex ecosystem. And what we didn't even talk about is the materials ecosystem that fits into this.
So let's talk about the materials ecosystem. Like, who makes this silicon? Where does it come from?
So typically the silicon comes in as ingots. If it's a 12-inch wafer, you get 12-inch ingots, and they come from multiple suppliers and across the Japanese, the Germans, etc. And what happens is once you get the ingots, then they're cut, and then you get individual wafers.
And these are like monocrystalline silicon ingots.
Yes.
I mean they're defect free.
Yes, they're defect free as far as possible.
Yeah. Okay. Good. So there is the design to chip ecosystem, and then there is the processing ecosystem, there's a materials ecosystem. Is there any other ecosystem that we need to be sort of aware of in the sense of what makes the final end product happen?
Yeah, I would say that you now have on the manufacturing side also the customers who are consumers of these products, the folks who make the laptops or servers, etc., the motherboards and the motherboard designs. So you have an entire ecosystem of design tools and materials, etc., with the motherboards.
At the system level.
At the system level. At the same time, a step before that is before the part goes out to the customers, if you will, then you have to test the parts. So you have test board designs, and you have to design special chips to enable the testing of a new device. Then if there are companies like potentially Samsung or Apple, etc., who are so vertically integrated that they put those devices into their own components which they sell, as compared to some other companies like say Intel or AMD, who would then sell it to others who would then integrate them into their products, like a laptop or a desktop, etc.
Okay, so let's come back to the packaging part. So the packaging is a step that comes in after the wafer is made. That's in the processing ecosystem. In the processing chain, it's the wafer. You cut up a wafer to take out a core or a die, and then that's packaged. What is packaging? Why is it such an important element of the overall ecosystem itself?
So in its most basic form, multiple reasons why you would need a package. The first one is silicon by itself is very fragile. It cannot be put on a motherboard. There are some technologies to put a chip on a motherboard, but then what happens is the pitch, the connections at which these chips are, you have the individual connections, the pitch, what we call, is pretty fine. So you need some sort of a space transformer which translates the effective pitch of the silicon to the motherboard. So a package becomes an intermediary. So it serves as a space transformer, number one. Number two, it serves as a mechanical protection, if you will, to the piece of silicon. Number three, more importantly, for the chip to function well, you need to supply it power. So what you need to do is then what the chip enables you to, what the package enables you to do is put localized connections and things like capacitors, etc., so that I can now have effective power delivery to the chip itself and to different parts of the chip as and when the chip needs it, depending on the workload of what the chip is designed to do. Along the same lines, when you supply power to the chip, you also need to remove, it converts itself to heat, joule heating. So you want to make sure that I can dissipate that heat. Some of these chips today, some of these products today are pretty high in power. Some of these chips can go all the way up to 3, 4, 5, 600, 800 watts today. So then you have to cool these chips. So what the package enables you to do is, to summarize, one is space transformation. The second one is mechanical protection, mechanical integrity. Number three is effective power delivery. Number four, it gives you a way to dissipate the heat by putting in some sort of a nice cooling solution, a thermal interface material to dissipate the heat as much as possible. And the other one is that if I have multiple chips of different functions now being integrated onto a package, then the package allows you to control the form, fit, and function of the end device. So for example, I want something small into a cell phone market, then I can stack chips in 3D and get the form factor to be smaller. I can fit into a cell phone, for example. Or if I need, a lot more components integrated onto a big server chips, then the package allows you to integrate multiple components onto the chip itself. So there are a lot of different reasons why you would need a package.
So let's now talk about the evolution of packaging technologies, right? That I can remember discrete components being packaged discretely, like a resistor in a resistor package, and an inductor in an inductance sort of a package to go through the whole VLSI generation of chips. And today, tell us a little bit about the journey that, say a company like Intel or any other packaging player has sort of seen, someone like you.
Yeah. So I was fortunate enough to see this evolution of packaging to where it is today. Like you mentioned, in its most, I would say, basic form, you take a small chip with, say, 10, 15, 20 connections. You connect it to what we call a lead frame, and it's a piece of metal with, assume it to be like a wires coming out of a piece of metal, and then you would connect these chips, the connections on the chip, to the package using technologies called wire bond. So physically I would stitch it like wires. This is the most basic technology today. That technology is still here and still here to stay, because if you look at a motherboard or any kind of product, you have hundreds if not thousands of products on a motherboard which are wire bond packages today. Some of your power devices, etc., will still be wire bond. But at the same time, as my number of functions, number of IOs, the power requirements, the power and ground connections I need goes up, then wire bond, you have a lot of electrical parasitics that actually impact the performance with inductance, etc. So what you want to do then is they migrated to a technology called flip chip. So you can now put an array of connections on the chip, and then you would literally flip the chip and connect it to the corresponding mating, connections on a package itself. And these connections can go, 50, 100,000, 200,000 connections between the chip and the package. So between the package and the motherboard itself, you may end up with 5, 6, 7,000 connections. Wow. And that's that space transformer I talked about earlier. Now, at the same time, everybody's probably heard of Moore's Law. So what Moore's Law in 1965, Gordon Moore, one of the founders of Intel, postulated, it was more of an empirical observation than a scientific law. What he said his observation was, the number of transistors on a chip will double every 2 years. So if you plot that out, and if you just do a search, For Moore's law, you'll get a very nice semi-log plot of a straight line. But that's more of a self-fulfilling prophecy by the technologists, right? But at the same time, what happened was every time you go to a different node, it became harder and harder, like we talked about. So at the same time, there is the concept of something called Dennard scaling. So the Dennard scaling, what that postulated was, as you scale your transistors, your voltage scales as well. So that way, the power, as you scale of the transistor, the total power needed remains constant. And so that way, it kind of enabled Moore's law, so that with every successive generation, the power was kept constant, so we could really advance, the performance.
So the thermal management technologies did not need to keep pace.
Correct, at that time, up to a certain moment.
Okay.
Then in the mid-2000s, what happened was, as you keep scaling these transistors to be smaller and smaller, the leakage current out of these transistors started increasing. And that rate of leakage was much higher than how voltage could scale. So what happened then was you had now the penalty you're paying as you scale these transistors from a power perspective. So then, engineers are very clever. So what you ended up, and physicists are very clever. So what you ended up doing was you now had, voltage scaling. It was kind of going down. So you ended up with multi-core designs, multi-chip designs, and then they also kind of tapped the clock frequency to be about just, you could not scale it up. So before you'd be on this treadmill of, clock frequencies. When I joined Intel, the 386, if I remember right, was like 16 megahertz, the clock. And, then went to 33 megahertz and 66 and 100 megahertz, et cetera, and it reached a peak of like, say, 5-6 gigahertz. But then after that, anytime you increase the frequency, then you're paying a penalty. So what they started doing was architects started now partitioning the chips. So we ended up with multi-core designs and multi-chip designs. That now has sustained Moore's law, and some people in the industry call it beyond Moore, because now what you're doing is instead of scaling down on a single chip, you're now partitioning them into multiple chips and putting them on the same package substrate. So that is what the industry today, calls heterogeneous integration, where I can mix and match technologies, different nodes onto a single package, and then I can mix and match performance and capabilities too.
So in this whole packaging ecosystem, you referred to 3D packaging. Is that, what are we talking when we say 3D packaging? And I'm assuming that's the sort of the most current technology.
Yes. So the previous generations of technology, like I mentioned, like wire bond, will still be here to stay. And there is, and growth in that market too. But that's growing along with where the whole industry is going. Now, 3D packaging, as the name implies, you have active silicon stacked in 3D.
So individual wafers or dies would be all stacked up?
Yes, individual dies would be stacked up, and there are different ways how you can go get that stacking done. The most common application of this, and the earliest application, was in memory. So things like DRAM, some high bandwidth memories, you would stack individual memories with a controller chip, and then get a much higher, capability of memories in one component. So 256 gig, 512 gig would be a part of one big stack. On the logic side, if anytime you stack logic to logic, you have a challenge of thermals. How will I dissipate the heat? If I have a logic chip on top of a logic chip, then the chip at the bottom has challenges dissipating the heat. So typically what you would see in the stacking would be a memory chip on top of a logic chip. Ideally you want the logic chip on top of the memory chip so it can dissipate the heat from the top.
Right.
So those are the kind of things people look at.
How many dies are we able to stack in a typical package?
Today's technology has 8, 16, quite a few. And there are, in production, a pretty high number of...
and this
is in memory. This is in memory.
In memory. Okay.
In logic, it's still a challenge to stack logic, like I said. So that's the big challenge is stacking.
Okay. I have a somewhat of a naive question. When I open a laptop motherboard, I see large, chips, as I call them, but I also see discrete components. Once I know a design and once I know I'm going to produce tens of thousands or millions of this design, why has the board not completely gone monolithic?
Cost. So remember, this entire industry is to do with cost. Moore's law is an economics law. It's not a technology law.
Okay.
Okay. So the bottom line is scaling. If you look at scaling, if Moore's law postulated that silicon would scale every 2 years, then by extension, just by observation, packaging scaling is typically every 4 years, and motherboard is every 8 years. Okay. So what you don't want is, if I just need high density routing, high density placements for a small section of the motherboard, why would I penalize the rest of the motherboard with a high density motherboard and pay the price? It's not cheap.
So if there is a cost motivation to shrink the laptop itself, like for example, a mobile phone, or if I want to create a computer on a palm, what you're suggesting is the technological drivers are all in place.
So for some of those segments, you do have what we call high density boards, which is the next generation of motherboards. That's what is being used. So if you have, a form factor requirement where I have to be fairly small in X and Y, then there is technology that exists today. Again, it goes back to cost, performance trade-offs, form factor. You don't want to put a very, very high complex motherboard, which is very fine pitch, for a very large server board. That's why you end up with things like what they call interposers. So if I want a high density connection localized, I would then build an interposer, which is just below the package, and then that would be another space transformer going down to the motherboard.
Wonderful. Good. So let's recap. You have design, then you have the fabrication, the silicon fabrication, and then the packaging ecosystem. Let's talk about what sort of skills are required to be a player in, or to be a contributor in this packaging ecosystem. What sort of engineering do you see typically for people in this space?
And so in the packaging area, it's become a fairly sophisticated process in terms of technology, manufacturing, etc. And the packaging substrate itself is a multi-layered organic ceramic substrate. So if I start right from, if you take a step back and if you look at packaging itself, there are three main factories involved in packaging. One is where the package substrate is made. The second one is where the wafer comes in from, the fab. The third one is where the chip and the package substrate is assembled. Okay. So you have these three, and I'm not even talking about the fourth, which is the motherboard factory. Sure. So if you look at this ecosystem, just from a purely manufacturing process, equipment perspective, you need mechanical engineers, material scientists, chemists, physicists, all of them. I'm not even talking about the fab side, just in the packaging ecosystem. Yes. So any kind of engineering or sciences related to physics and chemistry, because you need polymer scientists, you need metallurgists. The connections are on the what we call first and second level interconnect between the chip and the package and the motherboard. It's typically solder type materials. You need material science there. You also have a mechanical integrity between the chip and the package. Once it's assembled, you have an epoxy which is kept underneath, which is flowed underneath. And for that, you need polymer scientists, you need chemists. So you see the entire gamut of electrical engineers, obviously, to the electrical design. Mechanical engineers, stress analysis, stresses, residual stresses are a big deal. Warpage is a big component of this. So you have mechanical engineering. I would say any engineering you can think of, chemical engineers, they all play a role here.
Is it fair to say that the largest numbers of people are employed in the design phase and in the packaging phase? Is that where you see most people?
No, I think what happens is things like VLSI design tends to get a lot of press, but the materials world, the entire ecosystem of new materials, looking at the transition in the industry to lead-free materials required a completely new set of chemistries and metallurgies. Getting into conflict-free materials, getting into now removing PFAS from organic materials is a big deal too. So I would say that materials technology associated with that, the resulting mechanical structural issues, electrical issues, electrical performance, looking at how do I quantify, as an example, dielectric constants. etc. All of that plays a role today.
You're suggesting that the packaging slice of the bigger pie is actually one of the largest employers of the whole value chain.
Yeah, the silicon fab obviously takes a lot of people too, but
Those should be fairly automated, though, right?
they're automated, but still to come up with the initial process. We talked about how
Okay.
long it takes
Okay.
for the development. I'm not talking just the high volume manufacturing factories. My focus is more on the development of the processes, the materials, the design of the equipment, and don't forget the measurement tools, the metrologies too. That's an entire area of optical sciences, optical engineers who are needed. Their sensors. That's another area too. So it's a lot of good. An interesting example is that there was one time where we hired a whole bunch of folks from the aerospace department. And they visited, why would an aerospace engineer work in the electronics industry? So some of the processes we have are fluid flow processes. So I needed them for doing CFD type work. So we did a lot of CFD type work to optimize flows, the nozzles, the nozzle design, nozzle placements, and taking to the next level of how you would basically optimize performance and cost and throughput time.
In one of our previous episodes, we had Professor Bhagat Samakia, who spent a lot of his life, a good part of his career on CFD of electronics. Let's step back and talk about students. And what skills do you suggest students should acquire while still in college or in the early days after college? What does it take to get into this sector?
So I think apart from your regular degree classes and your core classes and your electives which you need to take, I would say a few things related to get as much as you can of project experience. What I mean by that is internships, or if there are specific elective classes which have project work on the side where you go and you build something, or using simple kits to make some things, or 3D printing. You just get your hand dirty. That's one piece. The second piece is in terms of design, etc. Learning skills like MATLAB or Python, or things like LabVIEW if you're doing a lot of measurements. So I'm just giving examples, but there are numerous tools which are similar. I don't mean to endorse just one set of tools, but there's definitely opportunity. Get your hands as dirty as possible in trying to make things and trying to get things just outside the normal classroom, right? That is one big thing. The second thing I would recommend is communication skills. That is something we typically don't learn in school, but that is something you get depending on your project. So, making presentations, but not just for the sake of making presentations. How are you giving the key message? How are you synthesizing your key thoughts? And, just simple things like presentation skills. Because what happens is when you go to work in industry or even in academia, as you well know, conveying your thoughts with clarity goes a long way in convincing somebody of what your ideas need to be.
Especially in the written form.
Exactly.
I see that as a skill that.
Exactly. And then, there is this whole thing about AI and the role of AI coming in. You want to be cautious about how you're taking advantage of AI because there are obviously, things you can leverage AI for the right reasons and then for the wrong reasons. How do you want to leverage AI moving forward? How do you make your work easier with the benefits of AI? Data analysis. Statistics is another one where if you've not had a rigorous class in statistics, I would highly recommend that you at least get a course on statistics and if possible advanced statistics, because everything you do related to manufacturing will have a statistical component to it.
Sure. So if I'm a chemical engineer or a mechanical engineer or a material scientist wanting to come into semiconductor packaging as a profession, how much electrical engineering should I know?
That's a great question. I would say you don't have to be a PhD in electrical engineering, but I think having a good understanding of just the basics of, say, transistors, electromagnetics, I think doesn't hurt. You don't have to have it, but I think it definitely doesn't hurt.
Can you help us with some choice electives that I can take as a mechanical engineering student, electrical engineering elective courses that you suggest would place me well?
Yeah, so I would say the basics of semiconductors, for example, right? If there's a class offered there, I would say take that. Basics of electromagnetic theory. So, take that class. Now, it doesn't have to be that you need an electrical engineering background, because the job you may get could be focused very much on materials development. But let's say the materials you're developing is a dielectric material, then it's good for you to know, hey, what happens to dielectric constants a function of frequency, for example. So those are the kind of things you would like to know so that you're a better engineer and a more well-rounded engineer.
And also, again, my outside-in view is that you are operating in a sea of electrical engineers, so you have to be able to speak their language.
Not necessarily.
Okay.
So if you're in the assembly and test world, you're actually in a sea of mechanical engineers and material scientists.
Okay.
Electrical engineers tend to be in a minority.
Okay.
Okay. So it depends on which area you're really entering. The perception is that you have to be an electrical engineer, but that's more in the design and VLSI and the chip design phase. But again, if you're working in package and package design, it's an electrical, mechanical, thermal design. It's all put together. You want to make sure that at least you have a good understanding of some of these variables so that you become a better engineer if you're in the designing of a package, for example.
So let's talk of the tools that are used in this whole world, right? You talked of how the tools have become far more end-to-end integrated now. When you say end-to-end integrated, you mean from the electrical functionality end of things all the way to the mechanical robustness and the process modeling as well, probably. What does one do to gain an understanding and capability with operating these tools?
So this is my opinion, is that the tools are not as seamlessly integrated as advertised, but nonetheless, they have good interfaces by which you can translate data from to the. As an example, I started with electrical simulation, and that ends up, with a thermals result. And that thermals becomes now the input for a mechanical response of a thermomechanical response.
Is that still how design is done?
No, you still have, then there is things about multi-scale, multi-physics tools, etc. And depending on the application, some of them are seamless, some of them are very painful to go and integrate.
So does the VLSI designer even worry about the thermal footprint when they are doing the VLSI design?
Good. So increasingly, yes. So, for example, there is a concept called thermally aware chip design, chip layout.
Okay.
So where the individual units are placed on the chip itself. If you don't want to keep two regions of, say, high power, what we call hotspots, next to each other, if there is a way to do that in floor planning without impacting the overall performance of the chip, then you keep them far away. So those are the kind of empirical rules or capabilities that are now being pushed upstream so that you're optimizing it, up front. So that definitely is happening in the industry today.
Okay. So back to the tools. Are we talking, are there places I can go to become more aware of the tools?
Yeah.
Become versed in the
Yeah.
tools?
So I was going to make two more comments there. The one is also, you talked about manufacturing process simulation.
Yes.
So some of these software companies are getting more and more into manufacturing process simulation, using things like recently agentic AI is an area where has entered manufacturing optimization. I'm just seeing increasing awareness of that. We don't have tools off the shelf to a large extent, but that's an area. Independent of all of that, these tools will come and go in terms of which vendor, who uses which tool, etc. My guidance is pick up the fundamentals of the modeling itself, the physics behind it. So, for example, if you're an electrical engineer and you want to get into packaging, and then you have to, I would say then the tools you need are computational electromagnetic tools. If you're a mechanical engineer and want to do things like stress analysis, then make sure you understand finite element analysis as an example. That you need to understand what is finite element analysis and not just be a button pusher, think I have this commercial tool, I will input boundary conditions, I get it automatically from my mechanical CAD design, I input it, it creates this mesh for me, I hit a button, I get an answer. I think what is needed is a better understanding of what are these boundary conditions, and making sure you understand the physics behind the computation itself, be it a chemical simulation, a CFD simulation, a mechanical stress, electrical, what have you.
So the knowledge of the tool itself, are you arguing that is not a prerequisite to an entry-level job?
Correct. Now, if you have access to a tool through your university and vendor X or vendor Y's tools available to you, by all means use it. And so that it kind of adds to your resume.
Because sometimes that's a privileged access.
That's exactly. So, but if you get a chance to do that as a function of a class or a project, it goes to my project emphasis too. Then you're one up on so-called competition of your peers, where you add that to your resume and say, I know tool X, I know tool Y. But independent of that, I think it's more important to kind of state in your resume, I know computational electromagnetics, I know finite elements, and I can pick up a software that's the interface, within a short time.
Wonderful. That's a very good take-home message for a lot of students out there. Let's talk about this semiconductor, the large ecosystem. We hear some of the names that we took early on in this conversation. It feels like this is a big player domain. But you also, somewhere along under a breath, said startup.
Yes.
Okay, so let's talk about that. What are some innovative ideas that a startup could potentially champion in this space?
Okay. I will give you my own personal experience. My experience has been there's been a lot of opportunity in sensors or optical measurement devices, for example. You have the big players who are the big tool vendors, and my focus has been to a large extent modeling, simulation, measurements, etc. And what I see is opportunities for startups, apart from the manufacturing area, for things like, let's say, we can break it up into multiple areas. You have a new way of modeling things. Be it electrical or thermal or mechanical or CFD, you come up with a fast algorithm. And I can now speed up computation by 2x and get almost the same accuracy, a little bit less, some trade-off in accuracy. That's a winner, right? Now, the challenge you have there is if a company, you're trying to sell that tool into a company, it's very hard to replace the incumbent tool in there, the software. So then you have to have a convincing argument of why your tool is going to be better from the software side. Measurement side, there are big players out there who work on their own research and R&D and coming up with the next generation of metrology tools. But at the same time, I have seen a lot of great startups and I would say small companies who have done some very good work in coming up with new ways of measuring things, cheap ways or fast ways. And that's another one I would definitely. The third one is materials, right? And there is a lot of talk today about thermal interface materials and, there was at one time a lot of talk about graphene and nanotubes and now diamond and then microchannels for cooling, just if the thermal space, for example. So there are startups looking at single-phase cooling and two-phase cooling, looking at localized pool boiling as ways of effective heat transfer. Coming up for these high-power devices. So I would say there is opportunity for startups in these niche areas where you don't have to be a big person on the block, but there's definitely opportunity. So materials, measurements, simulation, all of these things. So I would think of these top of my head. I'm sure there are a lot more.
Wonderful. Let's come back to India. India's own semiconductor ambitions. You've been an outsider studying these ambitions, and you've also been sort of an insider helping India scale up in some ways. Tell us, where are the opportunities in the short term for India and in the longer term?
Yeah. I think from what I've observed, like you mentioned, I am involved in a few of the initiatives. And I think one is the OSATs, or the assemblies we talked about. And I'm seeing a lot of excitement and also investments across India related to assembly and test, which is the back end of the operations. Sure. And that has a lower barrier, if you will, from a capital to get in compared to the silicon side. So it's still expensive. It's still not cheap, but at least that's a good place where I see entry there. You'll definitely need engineering skills for assembly and test, like we talked about, which is my home turf of packaging. right? Now that packaging, you start off with something that is not super advanced, but definitely an opportunity where you will see research in India. There is excitement in India there. Academia are definitely paying attention to it. I'm very aware of the hub and spoke model from the central government, where they're trying to fund some of these activities. So there is an effort for packaging research too across academic institutions, and that's in the process of being scoped out in terms of where the funding needs to be. So that's one area. In terms of the other area on the semiconductors, I'm also seeing a lot of activity where fabs are being set up, excuse me, like in Sanand, Dholera, etc. So that ecosystem, I think, requires significant amount of capital in orders of magnitude more. So you'll see that also come in, and there is a serious intent, I think, from the country itself to grow in that space. I'm seeing interest here from this institution where they want to put up a little fab for training purposes too. Those are the right steps to go, I think, and build up the workforce at the same time invest in capital.
So in the OSAT space itself, OSAT, I'm hearing you say, is a little bit like a low-hanging fruit for India, and then sort of grow backwards, into fab and design. Is there a sequential process to really get to the design, or can we leapfrog and build design capability in India ahead of becoming a fab player?
India is already a leader in design.
Okay.
India, if you look at the multinationals, the companies we talked about, who are doing chip design, they have a huge number of people already here doing cutting edge designs. So some of the leading processors in the world are designed or co-designed with India already.
So what you're saying is there is design capability. So there's design in India already happening. Package in India is likely to happen very shortly, and the fabricate in India will come in when there are plans for that as well, and that will sort of ensure the complete end-to-end ecosystem for make chips in India.
Correct. And to add to that too, the last step, which is the motherboard assembly process,
Yes.
right? That is already here and being invested in even more now. As many people know, a lot of the iPhones are assembled in India. You have other components being assembled on the motherboard level. So those are called EMSs, right? Those kind of that kind of manufacturing is already happening in India. Designs for that is happening in motherboard designs happens in India. So a lot of the ecosystem is already happening in India, and I think there's a lot of opportunity for growth even beyond this.
Wonderful. I think this clearly is a human intellectual capital driven effort. So where there is a high concentration of good human intellectual capital, the industry players are all going to have to gravitate to that location. And in that sense, India has a natural locational advantage, so to say. This has been a wonderful conversation, Gaurang. Thank you so much for helping pass this very complex space in a language that I think our students in India can wrap their minds around and potentially make informed career decisions to choose to go into this space.
Well, thank you. It was a pleasure. It's a pleasure talking to you.
Thank you again. This has been another episode of the Professor Mahesh podcast. Thank you all for listening. Until we meet again, be well, do good, and keep in touch. Goodbye.